Good evening. Today we will we will see the proof of the Lebesgue theorem. Remember that n measure 0 is defined as that for every epsilon positive, there exists an countable family of cubes or blocks, let's say from 1 into infinity, such that, well, it is a cover of df, meaning that df is contained in the union of all of these cubes, and this series of volumes of the cubes is less than epsilon. So let's define a set. Let's say that we have some natural number j. Then we define the set d of j like this. This is a subset of the domain such that the oscillation of f at the point x is greater or equal than the inverse of j. So you know, this oscillation is defined, just to remember, this is defined as the infimum of the oscillation of f in the domain intersected by a ball with radius delta centered in x, and this such that, well, this is positive. So it is the infimum of all of these, well, functions of all of the restrictions of f into neighborhoods of x with a decreasing radius. So this is interesting because you are saying that this oscillation should be greater or equal than the inverse of j. And you know that if we take j equal to 1, then this will be 1. And if we keep this index going into plus infinity, then this will tend to 0. So we have that. And then we have that the points in which the function is not continuous, which we define above, then this is covered by this infinite union of families. And this is so because you need to also remember that f is discontinuous at x if and only if the oscillation of f in x is different from 0 or greater than 0. If it is 0, then it is continuous. So since d of f is the set of points in which f is discontinuous, then for every point here, for every x that is in this set, then its oscillation, the oscillation of f on this point should be greater than 0, and then there will be j such that this holds. There will exist some j node in such that this oscillation is greater than the inverse of j node. So this is why this inclusion is met, is fulfilled. So we have that. Let's highlight it here. And then if we prove that each of these sets has m measure 0, then this whole union will also have m measure 0. And this is also because you need to, this is a property, let's highlight it here, and there is another property that tells you that the union or the countable union of a family of sets with n measure 0 has n measure 0. So this is a countable union. Then if we prove that each set D of J has M measure 0, then the whole union will also have M measure 0. So we will work on these sets. So the problem is translated into proving that each of these sets has M measure 0. So continue. We have arbitrary index J, and let's say we have an arbitrary epsilon that is positive. By hypothesis, remember we are working on the assumption that f is Riemann integrable. So by hypothesis, there will exist some partition of the domain such that the oscillations of f in each of these blocks of the partition, of subblocks of the partition, times the volume of each of these blocks will be less than this value. And recall that this is a characterization of the functions that are Riemann integrable in some block. F is E for each epsilon that is greater than 0, in this case epsilon divided by J. There exists a partition such that this oscillation it's less than that epsilon. So we are, if we are assuming that this is true, then it holds the other side of the biconditional. So we have this, and now we define the following set. Let's say we have a set I that is a subset of the indexes of well, this is a finite, since this is a partition, each of these subblocks, well, this family of subblocks is finite, so let's say I goes from 1 into k. This I will be 1 into k. So we will work a subset of I, this is here, such that D of J intersected with the interior of the subblock is different from 0, from the empty set, I mean. So you know that this is fixed because we choose one natural number at the beginning, and we will consider each of these indexes whenever the interior of these blocks it is intersected with this set. So this an important question will be: is this set different from the empty set, or it could be equal to the empty set? Well, it could be the empty set, in fact, because let's say that the oscillation, what happens if the oscillation of the function in the whole domain is half? If this happens, then the set D of 1, and by that I mean the set in which the oscillation in the punctual oscillations are greater than 1 will be the empty set, because you need to recall that the oscillation at one point are always less or equal than the oscillation at the whole domain. So we have half here, and we need, this cannot be greater than 1. So this could be empty, but for some values it will be different from the empty set. So now for a point that is in this intersection, I mean that is here, it will hold that is greater than the oscillation, this by definition of the J, and then this is less or equal than the oscillation here, because X is in the interior of this set, right? So then perhaps I need to highlight that property. Let me write it here. If J is a subset of B and X is in the interior of J, then the oscillation of X is less or equal than the oscillation of Y. There is a property. So it's given that we are in the interior of B of this subblock, then it holds. So continuing, we can say that multiplying, or well, summing multiplying this term by the volume of B of the subblock, then well, and this here will be less or equal than these variations here times the volume, and this is less or equal than the whole sum. And this is less than epsilon divided by J. And why is that? Well, because in the points in which the intersection of D of J with the interior is equal to the empty set, then, so I mean, for the points of this set, for every index here, the oscillation, you know that this is mod or equal than 0, and this is also mod or equal than 0. Then if we sum this set by this other set with the oscillations times the volume, then this is less or equal than the this set summed by this other series, so we can complete the whole summation. And then by hypothesis, recall that this was true, so then this is certainly less than epsilon divided by J. So it holds, or this implies that this is less than this set. So this volume will be less than epsilon. So we have this here. All right. Now, you need to recall that this set is included in the following set. The interior of V intersected by this one, and this intersected by this one, because if you know that each of these blocks is a closed set, so it will be equal to the interior, the union of the interior with its boundary. So the union of this set with its boundary is equal to this subblock. And then what happens when you well, remember that here, and remember that this set was in the beginning set as a subset of B. So this set, this D of G, it's always included in this union, because this is a partition of, well, not exactly a partition, but something like a partition of the set B. So if we take only the points in which the intersection of this with B is different from 0, then nothing is loose when we restrict this union to only I. This is recall the whole set of indexes. So this is what is being done here, only that we divided by each of these subblocks with its interior and its boundary. So then this whole union is included in this other set, the interior of B united by this set here. But you know that, and the set Y is equal to, it is like this, and this set is the union of the boundaries. So this is what is happening here is that since this is the intersection of the interior with D, then this is included in the interior of this, because you know that a set intersected with another set is always included in one of those sets. And the same here, this set here is included in the boundaries. So we are taking this here, and this set is the intersection of, the union of all of the boundaries. This is a countable union, and you need to remember that the boundaries of blocks is a union of degenerate blocks, and degenerate blocks like faces or edges or vertices always have n measure 0. So this is a countable union of sets with n measure 0, so this has n measure 0. And then this interior, this union of interiors also has n measure 0, because this set is covered by the union of the blocks like this, and the sum of the volumes of these blocks is less than epsilon for any epsilon, so this also has n measure 0. So the set D of J is included in the union of two sets of n measure 0, that is a set of n measure 0. Then it has n measure 0. So we conclude that this set has n measure 0. And then, since here the set of discontinuities was included in the countable union of set with measure 0, that is a set with n measure 0, then this set also has n measure 0. And so this concludes the first part of the proof, and we will go now with the other implication. So suppose now that D of f has n measure 0. And now we wish to prove that f is Riemann integrable. Now, let's say that k is equal to the oscillation of f in its domain. Recall that at the beginning we said that f is a bounded function, so its oscillation in the whole domain will be a real number. Now let epsilon be any positive number, then there will exist some countable collection, let's say from this into infinity, of open cubes. Recall that the definition of n measured 0 can be taken when the cubes are open or are closed, when all of them are open or closed, or even if the cubes are blocks, n blocks in general. So here just consider that they are open. So they are open cubes such that this set is covered by this union, and the sum of the volumes is less than epsilon divided by 2 times k. So we took an arbitrary epsilon, and now we're dividing that by 2 times k, which is a fixed, of course. So now take a point in its domain where f is continuous, i.e. in its domain minus the set df, the set of discontinuities, and then we will show that there exists some cube, well, m cube open, such that the oscillations of f in the intersection of this cube with the domain, well, let's say x, is less than epsilon divided by 2 times the volume of P. So this is the volume of the domain, which is given. This is fixed, so it's okay. And we will prove that this set exists. We wish to prove that. So recall that since x is in this set, i.e. f is continuous in x, then the oscillation of f in x is equal to 0 by definition, or well, by its equivalent. Then recall that the oscillation is the infimum of the oscillation in neighborhoods, so this will imply that there exists such that intersected by this is well, less than why? Because this is a number that is greater than 0. So since 0 is the infimum of the set of these oscillations, then this cannot be a lower bound of the set, because the infimum is already 0. So this implies that there will exist an oscillation that holds that it is less than this value here. This by definition of infimum. So what happens if we take our cube that we wish to define here, because you know this is a ball centered in x, then in every ball we can always draw a cube inside of it. So this so defined cube, open cube, it holds what we wish to prove here. this thing. You know, it went just by definition of infimum. So now for every point in which Vf is continuous, there exists a cube such that this holds. Now, continuing, we need to observe also that the domain can be written like this. And then this is in turn included in this set. This is because this set of discontinuities was covered by this family, the family that we defined at the beginning. And then this set is also covered because, well, I didn't say that at the beginning, but these cubes are centered in, let me write it here. So X is included in each of these cubes. So the center, these cubes are centered in the origin of the balls. So each point of this set is included in one of these open cubes. So the whole set can be covered by a union of, let's write it here, the union of X in like this. But recall that V is a compact set. So since this is a union of open sets, and this is also a union of open sets, then this is an open cover of V. By V is compact. So you know, by the characterization of compact sets, there will exist a finite subopen subcover, i.e. that V is included in some M2K, the union of this set, let's put it like S equal to 1 into R, like this. Now we define a partition, let's say some partition like this, such that for each subloop it's included either here or it is included in one of these sets, and it may be could it be included in both of them? Well, perhaps. It is not forbidden, but it doesn't really matter. Then what happens if we define a set I like this? Well, let's say that once again this capital letter I is a set of indexes of P, of the partition. Then this set will be such that it is included in one of these, or well, let's say if there exists a J in the set such that B is included here, and by J we will say this is a subset such that there exists an S in this set such that is included in this one. So the sum of the variations of this is less or equal than, well, this here, let me copy it here, plus the variations in J. But now the variations here, you need to recall that what happens if these subblocks are included here. Well, you need to remember that each of these is less or equal than the total oscillation, which we denoted as k, recall in the beginning. Then this is, we can, since this is a constant that doesn't depend on the index, we can write it like this. Plus, now since this is included in, well, this is included here, well, like this, more like this, better like this. And then this was less, so this is also this also doesn't depend on the index, so we can put it outside of the sum. This will be plus the volume of P. Now recall that here less than epsilon divided by 2k, because each of these volumes is less than the volume of Ci, well, C of G, and the sum of these volumes is less than this. So this is strictly less than k times this, plus, and on the other side the sum of all of these volumes will be less than the total volume. So this cancels here, this also cancels here, and then this is less than epsilon. And since we found a partition such that this is less than epsilon, then this implies that f is Riemann integrable in the block V.